Marco Piva from Penn State University. He will speak about one loop effective action of quantum gravity with Fakeons and its phenomenology.
Okay, thank you. Hi everyone. So this talk, I will tell you about this new model of quantum gravity, which is based on the idea of Fakeon, or a fake particle. I will tell you in a moment some details about this thing. This new degrees of freedom that you can have in quantum field theory is brings a solution of the unitarity problem that is present in higher derivative models of quantum gravity. And in this way, these Fakeons, they reconcile renormalizability with unitarity. I will tell you also some phenomenological consequences about this effect, about these things. So first of all, just to clarify what I mean with the problem of quantum gravity and renormalization and so on, renormalizability in quantum gravity is a problem in the sense that Einstein gravity is unitary but non-renormalizable. So in the effective action, the counter terms have infinitely many. You have infinitely many types of counter terms, each of them with a new coupling. So you will need to measure, in principle, infinitely many couplings. And this is the problem of non-renormalizable theories, that at some point your predictive power fades. On the other hand, there exists already since many decades a possibility of making an extension of Einstein gravity, which is then renormalizable, which is known as a stellar theory from Kelly Stelle that developed this theory. The effective action has counter term which has the same functional form of the classical action, and is this one, so you have to add quadratic terms in the curvature and the cosmological constant. The problem of this theory is that it's non-unitary. So this new idea that I'm going to explain now will fix this apparent incompatibility. So it looks like unitarity and renormalizability are mutually exclusive, but in the end it turns out that they are not. So let me say first something about unitarity very briefly, because later also Damiano will say something. This unitarity is a condition on the S matrix, which in terms of its non-trivial part, T, can be written in this way. So you see it appear the imaginary part of T. In quantum field theory, in any quantum field theory, there exists a set of identities, which are called cutting equations, which are valid always, and they can be recollected. They are diagrammatic identities, so you have these identities diagram by diagram in perturbation theory, Feynman diagrams. They can be recollected in an equation which looks like this one. So it resembles actually the unitarity equation, except for this matrix H in between. So the point is, if the degrees of freedom of your theory will lead to have an H which is equal to the identity, then your theory is unitary. Or, in another point of view, if you can project consistently on a subset of your degrees of freedom, and now we'll later say what means project consistently, you will have a unitary theory. All of these minus signs are caused, in general, by potential ghosts. These are the degrees of freedom that usually causes the violation of unitarity. So this is what I mean with unitarity and what I am trying to fix. So what is a Fakeon? I will tell you very briefly the rough idea. There are already several papers published by Damiano and by Damiano on the detailed formulation. I'll just give you the idea to understand. So usually in quantum field theory, you have to give a prescription for the propagator when you want to do perturbation theory. And fixing a prescription for the propagator, which is an object, now I'll tell you about scalar theory, a massive scalar theory, but everything applies in general for spin, for any spin. Spin 0, spin 1, spin 2, and fermions. But I will take just a scalar example. Usually is an object of this type, which is, as a distribution, is not well defined, and you need to give a prescription. Usually the prescription on the propagator have an impact on, gives you a prescription for the scattering amplitude as a complex function. So let's see what happened in the standard cases. So when you have a propagator like this one, so with +1 here, and you use the plus I epsilon, the final prescription for the propagator, on the side of the scattering amplitude, what you're doing is to prescribe this function, which can be seen as a function of complex value, complex variable, which in general could have some branch cut. And when you have branch cut, you need to give a, let's say, a prescription how to you define your function on the cut. So the final prescription at the level of the amplitude tells you that you have to do an analytic continuation from above the cut. Of course, if you do the other way around, the result will be different. But the final prescription gives you this. Now, it gives you the same, usually if you do the same quantization for degrees of freedom which has a propagator of this form, so with a minus here, which are usually called ghost, then you have to do the same thing, of course. So in this case, we say that we have a particle. In this case, we say that we have a ghost. Both cases, because the prescription is the same, have this effect on the scattering amplitude, and the physical effect is that above this threshold, a physical threshold, there will be production of such degrees of freedom. So in this case, you will have production of particles, and in this case, you have production of ghosts. Problem of ghosts is that they bring to violation of unitarity, in the sense that I told you before. Plus, you can see ghosts in many different ways, and see how they bring inconsistencies in the theory. So what is a Fakon? A Fakon is a new type of degrees of freedom, so it's not a particle, it's not a ghost. And to obtain a Fakon in a quantum field theory, you have to prescribe the propagator in this way. So you first multiply and divide by k squared minus m squared, and then you deform it, introducing a fictitious scale, capital epsilon. Now here you note that you can do this prescription for both signs, so you can make something that would be a particle in a Fakon, or something that would be a ghost in a Fakon. Of course, the main application of this is to turn what usually is a ghost into a Fakon. How this have an impact on the scattering amplitude? So if you use this prescription, which is not just like this, the story is a bit more complicated. You have to do certain domain, certain deformation in the integration domain, in the Feynman integral, which I don't give you the details now, but you can check, for example, this paper. This is doable, let's say, at the level of the prescription of the propagator, so you make computation, direct computation of Feynman diagrams using actually this propagator. It's still doable, but a bit complicated because all of this deformation must be found for each diagram, so it's a bit involved, but still doable. Anyway, it turns out that this prescription with all of this deformation thing, at the level of the amplitude, is just the average of the two possible prescriptions, so the analytic continuation from above and the analytic continuation from below. So it's just the arithmetic average. This is very powerful because you just, in the end, you can just compute your theory in the Euclidean space using usual technique. And then, if you want to quantize some degrees of freedom as a Fakon, for example, a ghost, which would violate unitarity in your theory, you apply just this average prescription. To give you, again, a rough idea, this prescription is real, so it will not, the particles which are, the degrees of freedom which are quantized with this method will not contribute in the imaginary part of T, what I showed you before, so there won't be a violation.
Sorry, just to understand,
yes.
Is this prescription for the amplitude automatically you're using the Fakon?
Yes.
So
that's
one-to-one
yeah. So all of this deformation is exactly like doing this. It's shown in very details in this paper.
Sorry.
And yeah.
So you add this particle to the theory? So
No. When you have some particle that you, let's say, they cause some inconsistencies, like the ghost in higher derivative theory. Instead of using the Feynman prescription for those degrees of freedom, you use this new prescription. I'll show you now the details in an example. And yeah, so this capital epsilon plays almost the same role of this small epsilon. So you do the computation and then you send this epsilon to 0 at the end. And the result is this one. So let me show you a very simple example in a scalar field theory, massless. Let's say you want to compute Babbo diagram, this diagram, in this theory, 5 to the 4th. And then I want to compare now what happens if you use the Feynman prescription for the scalar degrees of freedom, or if you use the Fakeons prescription. So after subtracting the divergences, now I'm looking at the finite part, at the one loop amplitude. With Feynman prescription, which at the level of the amplitude means analytic continuation from above, you get this result. While with the new prescription, the Fakeons prescription, you will get this result. So let's see in detail what's the difference. So usually here, you will have a threshold that in this case is p squared equals 0. Then if you are below the threshold, so p squared negative, minus p squared is positive, and this I epsilon is redundant in this thing, because you don't need to have a well-defined logarithm, you already have, because it's a logarithm of a positive quantity. And then you don't have an imaginary part, and you don't have any contribution in the unitarity equation, and which means that below the threshold you will not produce these degrees of freedom. As soon as the threshold, you are above the threshold, which is p squared positive, this quantity is negative, and you need a prescription for the logarithm. And this generates the branch cut. So in this case, when you are above the threshold, which is the branch point of the branch cut, you will produce, physically produce in scattering, these degrees of freedom, the phi. Now what happened here? Here, you see, if you are below the threshold, so p squared is negative, but there is another square, so it's again positive, and you don't have any contribution, and you don't have any production. If you are above the threshold, p squared is positive, again, this quantity is positive, you don't need any prescription, you don't have an imaginary part, and you will not produce this particle. So the effect is that despite there are some branch point and branch cut associated to this Fakeons, they will not be produced physically. They will not belong to the asymptotic spectrum of the theory. Now this is a very simple example in which I turn all the degrees of freedom, which is just one scalar field, into a Fakeons. And it's just to compare the two possibilities. Now I will make a mix of things in gravity. So let's consider this action, which is the one that I told you is renormalized.
Just to follow.
Yeah.
So in the case of scalar theory, the Fakeons prescription doesn't give physical amplitudes.
It gives a trivial theory. It tells you that it gives you a trivial theory. Because if you, you said in the case of scalar, yeah, in this case, if you just have one degree of freedom, you quantize it as a Fakeons, so it doesn't appear as external state. So the scattering matrix is 1, is the identity.
So it's not the usual theory.
What?
It's not the usual theory.
No, it's not. It's different. It's different. But now the key point is to use it in a mixed way. So for when you have more degrees of freedom. So in this case, you have more degrees of freedom. Some of them are okay. Others, if you use the Feynman prescription, are ghosts. So this is the stellar theory, the same action, same classical action. But now I will show you with some detailed computation of one loop quantities. That is actually, at least in principle, physically different if you use this prescription. So how you use it? So now I'll show you just an example where there's no cosmological constant, and this I use this identification, but it is just to simplify the expression. And we have the full formula for the most general propagator. So if you write down the propagator of the graviton, you have something like this. This scalar part is a crucial point now. You can decompose it. Now you see explicitly, this is before to choose any prescription. You will see explicitly that there is 1 degree of freedom, which is a massless one, and I have a positive number here, and this is the one associated with the gravitons. Then you have these other degrees of freedom, which are massive. This is the mass, And you have a minus sign, so you have a ghost if you use the Feynman prescription. Now what is the idea? Is to use a mixed prescription where you use the Feynman one for the graviton, because you want to produce graviton. So I told you that if you use the Feynman one, you will produce at some point above that some threshold, you will produce those degrees of freedom. And you want to produce graviton because you want gravitational radiation. So you use the Feynman prescription for this one, and you use the Fakeons prescription for this other one. The important point is that in this way you will not produce this particle, they will not contribute in the unitarity equation. They would contribute with the Feynman one, but they would contribute in a bad way. They will violate the optical theory and unitarity of your theory. And the crucial point is that despite you do this prescription, the renormalizability of the theory is not spoiled by this. So if the theory is the starting action is renormalizable, even if you choose this prescription, it will stay renormalizable. So in this way, you can have a unitary and renormalizable quantum field theory of gravity. So this is just a repetition of what I just said. In this paper, we compute, again, the one-loop beta function of this theory using the Batari-Minkowski formalism. This is just the result, just to show you that we have done that. Again, a rough idea of this is the following. As I said, you can use this prescription at the level of the amplitude. So you can just compute everything in the Euclidean. So you just perform till the end every computation, and then you rotate. You go to the Minkowski axis. Okay? You can do that with the Feynman prescription or with the Fakeons. Of course, if you compute everything in the Euclidean axis and then you rotate, if you have already subtracted some divergences, there won't be a generation of any new divergences in this process because it's a rotation. Yes?
In principle, you can have also the well tensor square.
Yeah, it's the.
It is protected.
No, this is by square up to total divergence. So it's actually.
Not free.
What?
Free higher order. No.
Free higher order?
Only three.
Yes, if you use, okay, you can make Riemann square, Ricci square, and scalar curvature. Then you can use Gauss-Bonnet, and, no, Gauss-Bonnet, that's enough, I think. And you remove one. Now this combination is the particular one which gives you bi square plus a total derivative that I just neglected. That's the most general one using all of these things in 4 dimensions. So that's the result of the renormalizability. So I'm talking about one loop in this theory. So from the side of renormalizability, one loop is exactly the same as the usual one, and in general, renormalizability is not spoiled by this prescription. Now, what is changed is the absorptive parts are the absorptive parts of the effective action. So now I'll show you first computation, which is in the case of this theory coupled to massless matter, any kind of matter. So some number of scalars, fermions, vector boson, and Pauli fields, and Procca fields. We use massless, but then we made another paper and we make the general computation when all the matter fields are massive. I'm just showing you this because I want to give you an example of a computation in this theory. And because when we add the massive term for each matter field, we have to do a field redefinition that I will tell you in a few minutes, so which complicates a bit some step to understand how you do the computation. Now it's just to give you an idea. So in terms of the diagrams, so one loop diagram, this is a 2-point one loop diagram. The relation between M, which is the amplitude, and the diagram is the following one. So, except for this sign, what is it? The imaginary part in the amplitude is the real part in the diagram. So I just want to show you that there's no real part in the diagram. So you have a one loop, so you have the product of 2 propagators, and then you decompose the 2 propagators, and you have the graviton part and the Fakeons part. And then you have all the possible products. So when you have a product which is fake, every time one of the degrees of freedom is a fake, you have to use the Fakon prescription for the amplitude. So you can have fake, so you use the average continuation, which is, this is how we call this arithmetic average of the two possible analytic continuation. This is real, so the amplitude is real, and there's no real part in the diagram, and it's purely imaginary. That's the same when you have one graviton and one fake. And the only non-trivial part is when you have a graviton and a graviton in both propagator, and you have to use the usual with rotation, so the Feynman prescription. In that case, you can just substitute the propagator with the gravity, with the one of general relativity, basically. So now I'll give you the results of these computations. So first is that the pure gravity contribution can be written in this way. So it's proportional to the equation of motion of the graviton. So they can be reabsorbed with a field redefinition, and this delta G is the field redefinition of the metric that you have to adopt. Then the contribution of matter is this one. So this is the matter plus gravity. So when you couple gravity with matter, you will have again this contribution, because it's the same, it's the pure gravity one. And then you have the matter contribution. Here C is the central charge, and eta is the nominal coupling for the scalar field. So this is how a typical computation of a one-loop diagram, in general of a Feynman diagram in this theory, would work. Now I'll show you the massive case. In this case, to avoid some complicated thing, we have to switch in another description, let's say using a field redefinition, and instead of having a theory of gravity which has just a graviton field and higher derivative, we have a theory of gravity with just two derivatives but more fields. So we introduce some auxiliary field to get an equivalent action. The auxiliary field are a scalar field, a spin-2 field, and then with this transformation, a Weiss transformation, and then field redefinition in the action, you get an action of this form. So the first term is the Hilbert term for this metric, so it's just standard general relativity. Second term is the action for this chi, then you have the action for this phi, and then you can couple standard model, which you can see there is this funny way of coupling things with the metric, because in particular the standard model is coupled with this combination of metric, which is the following. So in detail, the action for phi is just the same that you will see in the Starobinsky inflation, because that's basically, if you're ignoring the Ricci square part, or if you want the Weil square part in the action, then you have just r plus r squared, and that's Starobinsky inflation. And usually they do exactly the same transformation, but they don't have this chi, and you get this scalar field with this potential, which is a good candidate for inflation. So we just leave it like that, and then the additional part is this chi, which is a spin-2, massive. This is the mass term, and has this complicated action, which is must be expanded perturbatively. But the kinetic term is the same of Pauli fields, one, with a negative sign in front. So it has the wrong kinetic term, the wrong sign of the kinetic term. And this is the one that needs to be, that must be quantized as a Fakon if you want a unitary and renormalizable theory. So in this picture, we have a graviton multiplet. We have h mu, which is the graviton, this phi, and this chi. Now there are several possibilities that I will call in this way. So the graviton must be quantized as a graviton, so with the Feynman prescription, because as I said, you want propagating graviton degrees of freedom. So it's G. Then this phi can be quantized either as a Fakon or as a standard scalar, because if you look at this action, the sign of the kinetic term is the correct one. So you are free to choose to quantize it as a Fakon or as a standard scalar. That's something that must be confronted maybe with some experiment or some cross-check, let's say. So you can have a scalar here, while this other one, chi, since it has the wrong sign of the kinetic term, must be quantized as a Fakon. So you can have a GFF theory, GSF, so graviton fake fake, graviton scalar fake, or you can quantize everything with the Feynman prescription, but then you will have a graviton scalar ghost. And these ghosts, which are the wrong degrees of freedom, that gives you a non-unitary theory, will be propagating, and they will cause exactly this violation. So you can compute the absorptive parts again, but for this multiplet, so it's a matrix. We compute all the possibilities. So when you have H, phi, chi, everything. I just show you that the H1 is again proportional to the equation of motion, so it can be absorbed away with a field redefinition. And the matter contribution is a bit more complicated. You have these polynomials and this R, which depends on the mass of the field. If you send the mass of the field to 0, you will get again you will get the previous result of the massless case. So this is how this modifies. Now, why I told you all of this detailed computation? That's the reason. So these quantities, and in a minute I will give you an example, are related to actually physical quantities. So if a theory have these quantities different, so if you can discriminate these quantities in two different theories, then you can say that they are physically different. So this is the example, without giving you the details. They're not horribly non-local and not very nice to see, but the contribution in these three cases, which are the three possibilities that I listed here, are this one, and you can see that every of these three possibilities gives you three different possibilities, three different contributions. You will have more and more contribution if you quantize. The more you quantize the degrees of freedom with the Feynman one, the more you have contribution in this absorptive part. So that's how you discriminate. You can, in principle, discriminate theory. Of course, all of these quantities are related to very high energy physics experiments, which are not accessible now. And this is why I will tell you later something about cosmology, where maybe this theory can be tested, and also Damiano will say something about that later. So one quantity that you can relate to this absorptive part is the width of some field. So usually you can compute the two-point function of certain field. Now I'm showing you the two-point function of the Fakon field. And you can resum the bubble. You know, there is this geometric series, you can resum it, and you can have the corrected propagator. And from this corrected propagator, at the peak of the mass, when the energy is approximately the mass of this particle, you have this form, and you can extract the width of the particle. What is the of a particle in the standard case now is the width of the Fakon. So usually the inverse of the width is the lifetime of the particle. So this is the decay rate, or the inverse is the lifetime. So if you compute this for the Fakon, you will get this result, where C, again, is the central charge, and the point is that this is negative. That would be a problem. This is a remnant of the fact that chi would be a ghost if you use the Feynman prescription. But now chi is a Fakon. It doesn't appear as an external state, so it doesn't decay. It's not really a particle that you can say it has a lifetime, it has a width, or something like that. So what is the interpretation of this number? Actually, the inverse, the absolute value of the inverse of this number. So what would be the lifetime? I forgot one part. But let me finish. So this this quantity is related to the violation of microcausality. Why microcausality is violated when you have a negative width? That's very easy to see. If you take this distribution, You can see that is of the form of the Bright-Wigner distribution, which schematically is this one. If you anti-Fourier transform, you will get this quantity. If you consider that gamma can be positive, either positive or negative, then you will get this result. So you have gamma t inside the argument of the theta, which means that if gamma is positive, this thing gives you a causal Green function, while if gamma is negative, it's not causal. Because it will pick the future instead of the past when you integrate this Green function with the source of your physical problem. But anyway, it's a little bit of future because of this damping factor or because of this strongly oscillating one. So the inverse of this quantity, the modulus of the inverse, is a time, and the interpretation that we give to this is how long is the violation of microcausality. So if you want to reinterpret this, since chi is not a particle and gamma can't be really seen as a decay rate or the inverse is not really the lifetime, but it's a time scale associated to this thing. So what is the outcome of this theory? One of the outcomes of this theory is that at very small scales, which scale? The one of the mass, around the mass of this Facon, cause and effect lose meaning. So there is a fuzzy interpretation of the events, which is somehow something that you can expect from a quantum gravity theory. You expect to change somehow the concept of space. No? So in this case, it is like a generalization, maybe again very roughly, of indeterminacy, quantum indeterminacy. You're saying that you cannot determine the future without knowing a very, very tiny portion of the future itself, which is not which is why I'm saying that it is microcausality is violated, not macrocausality. And in particular, if you put some number here, we don't have any, at the moment, we don't have any bound for this mass, but this is just to show you that if you choose a mass scale for these masses, which are several orders less than the Planck mass, still very high, but Planck mass is 10 to 19, 18, 19, so it's 7, 8 order less. Still, you will have a violation of microcausality of these amounts, which is still in agreement with our experience of causality. So this mass can be really lower than the Planck mass and still have an effect which doesn't violate what we see about causality. This is another interesting thing. If you take the 2-point function of the Facon, of the resum Facon, and you send the width to 0, then you get a positive quantity, which is correct. And it is the usual quantity, the usual distribution that you will find in the case of a typical particle. So what is the meaning here? The meaning is that if in nature there is some Facon, so because this prescription applies in general, so it's very useful to turn a ghost into a Facon, but in principle you can turn a standard particle into a Facon and see what is the phenomenological difference. And Damiano published a paper about asking if the Higgs field, Higgs particle could be a Facon, for example. The thing is that the traces that Facon leaves are the same that the standard particle would leave in an accelerator. That's the meaning of this limit that I showed. So you would not see something strange after they are decayed. So it looks like that some particle has decayed. But still, it doesn't mean that you cannot really appreciate the difference between a particle and a Facon. Because they will contribute, as I show you, in the absorptive part in a different way. And those contributions affect some measurable quantities, like the width of a certain process. Another thing to show you again, some example to understand what's happening, is that in the case of stellar theory, if you take the 2-point function, the imaginary part, you will get a negative quantity, which is wrong result, the not unitary result. And roughly speaking, at the level of the of this optical theorem, the optical theorem is violated, and in this is just an example for this diagram in the case of stelle. So let's say that you have this scattering, and this curvy leg is a Fakon, is the ghost. When you use the Feynman prescription, this imaginary part will be negative, and this is shown here. Imaginary part of this thing, which is this diagram, is negative, while this part is necessarily positive because it's a modulo square. And this is how, in stellar theory, the unitarity equation, the optical theorem, is violated. Here, in the Fakon case, let's take this equation in the case of a Fakon. What happened? The imaginary part of the diagram is 0 because the prescription is real. So this is 0. While on the other side, this thing is 0 because this is the amplitude of having as an external state this thing in the incoming, but this thing in the outcoming. And as I said, the Fakon does not belong to the physical spectrum. So because of this projection, let's say, of the Fakon degrees of freedom, this amplitude is 0 by itself. So in the end, the optical theorem is not violated in the case of a Fakon because you have 0 equals 0. For these two reasons that I just told you. Now let's see very briefly what happened in the classical limit, because this prescription brings some remnants in the classical limit. So this average prescription reduces, the Fakon prescription reduces at the level of the Green function, the classical Green function, just as the average sum of the retarded and the advanced Green function. So let me give you a very simple example in classical mechanics, non-relativistic mechanics, with higher derivatives. So you have a standard equation of motion, but I add this additional higher derivative term. Then you can factorize this operator, and then you invert this operator by means of its Green function. So you put this on the other side, and integrate it. So you do the convolution of the Green function of this operator with this source, and then you get this. And you call this thing this average force. So instead of having F equal ma, you have average F equal ma. So this is the, and this can bring some different consequences in the classical, even in the classical limit. So in an analogous way, you can do the same with gravity, very roughly. And Damiano will give you an example in the Friedman case, where you have, instead of Einstein tensor equal to T mu nu, you will have Einstein tensor equal to some average T mu nu. And this average is made in a very similar way. Of course, here it's not linear equations, and it's a bit more involved. But let me say something more about this projection that I told you. So from the point of view of the space of states. So you can consider the space of states. So I'm constructing now the Fock space of your theory, okay? We have a metric space built with the states, with physical creation operators. Then what you usually do is to complete into a Hilbert space this metric space, and then you have V as your Fock space of the physical space, because you build that with the physical creation operators. What happened here? Here we have a bigger Fock space, which is the total Fock space of the theory, which is made by, is constructed by means of the creation operator of all the fields. So graviton, the phi, the chi, which is the Fakon, and maybe all the massive, all the matter fields. So what you usually do is that you have this physical space is a subspace of the bigger space, and saying that you do a consistent projection means that, saying that the theory is perturbatively unitary means that you do a consistent projection from W onto V. And consistent means it's not just that you are projecting the space, so you're just throwing away the degrees of freedom you don't like, because they will be reproduced in loop diagrams. The projection is consistent if you remove those degrees of freedom from the space of state, but you also implement some prescription like the one that we developed, which assure you that these degrees of freedom are not regenerated back in the loop equations, loop diagrams. So that's the meaning of this projection at the level of the Fock space. Now just one last thing about what I'm doing currently. It's just an idea, because I don't have a complete detailed calculation now. So to measure this effect, as I told you, all of these different absorptive parts that you can use to discriminate the theory, they are associated to very high energy physics. So we are trying to find some signature in, for example, in cosmology, where maybe it could be easier, let's say, to detect something. So if you consider a higher derivative harmonic oscillator, so it's just an harmonic oscillator, harmonic potential, standard kinetic term, and you add this higher derivative term, then you can do some field redefinition, and very similarly to what I told you when I introduced the phi and the chi, you reduce the number of derivatives and you increment the number of fields in a very similar way. And then you have Q, small q, which is a standard degrees of freedom, and then you have a capital Q, which is the wrong sign of the kinetic term. It's the ghost associated to this higher derivative term. Then you can compute the Hamiltonian from this Lagrangian using the Hamiltonian where the variables are the Q and its momentum and capital Q and its momentum. And you get this thing. Then you can do some symplectic transformation here to, let's say, diagonalize maybe the action, the Hamiltonian. And you get the two Hamiltonian of two different harmonic oscillator, and one has the wrong sign in front here. The interesting thing is that the new oscillators have new frequency, which depends in this way on the old frequency. Okay, and this projection means that you project away these degrees of freedom. So the projected Hamiltonian is this one, which is positive, definitely, bounded from below. Now the idea, and this is what I'm currently working, is that very similar equation, very similar action is present in the case of quantum cosmological perturbation around Friedman background. It's just that you have to do this substitution, so you have time dependence of all of these parameters, which makes these steps a little bit more complicated. But the idea is to find the analog of this capital omega and omega tilde and see what I have to project away in that case. So, conclusion. Thanks to this new idea that Damiano had in 2017, we performed a new quantization prescription. We developed this new quantization prescription, which reconciled renormalizability and unitarity in higher derivative quantum gravity. This theory is not so much more complicated with respect to the standard model, for example, so you can do actual computation, which you can discriminate from other type of quantizations. So this theory is predictive and maybe could be testable in the near future thanks to this, to the new studies that we are currently doing on cosmology. In particular, I'm doing these things, but cosmological perturbation in collaboration with Eugenio Bianchi at Penn State. And these Fakeons, this fake degrees of freedom, this fake prescription introduced this new degrees of freedom that was never found before. So we actually realized that quantum field theory can describe something more than particles, but also this Fakeon, which has a phenomenology completely different, and it's worth to study also this in general. Thank you.
Any questions? Please, yes.
Maybe I missed some point.
Mm-hmm.
So you wrote about the projection, so you have rewritten the expression model like without the twin function.
Yes, yes.
But that would not converge if this derivative term, like in effective field theory limit, I understand that makes sense.
Mm-hmm.
But if that is tau, tau times 1 over time, tau times energy scale, if that term becomes comparable to the other one, probably that prescription will not be comparable.
Why? I mean, I'm not doing an expansion. It's not an expansion. I'm just computing, this is a differential operator, and you compute the green function of this operator. That's it. You just do the
We
evolution.
want to solve it, no?
What?
We have to solve.
Yeah, sure.
In order to solve.
Ah, you mean you want to solve it per two? Yeah, sure. But now in our case, this is an example. But in the case of gravity, this tau would be 1 over the masses of these things, which is not comparable to 1, or to this energy state. Yeah. So that's the case. So if your point is that you don't know how to solve it, and yeah, sure. So you have to do some perturbative things, and now it's
I have a question. So all symmetry are respected in this description?
yeah.
Because it's a very similar situation happened if you do LIGO gauge. If you do LIGO gauge, you create spurious.
Sorry.
You create spurious force in your calendar.
Uh-huh.
Okay. And then you define a new prescription, which is called library of non-understand prescriptions, in order to define how to remove this spurious force. However, then when you try to do it loose, okay, then you have to modify this prescription in such a way that it preserves. I mean, it's very similar. I mean, it is a prescription about how to calculate the final diagrams around this force. Like axial force, but these are force along these axial gauge, okay, which are not physical ones. And then you have to do a similar prescription in order to define the final diagram correctly.
Okay.
But then there's a problem that you violate symmetry, so you have to restore the symmetry in order to. I don't know if it's similar situation.
No.
Well, the symmetry are preserved with this prescription.
Yes.
Even though you treat the different degrees of freedom in different ways.
Yes. Plus these degrees, I don't want to, these degrees of freedom are not spurious. I want to keep them. I want to keep just one part of their impact on the theory, which is they contribute to renormalize here. In that case, they are artificial, I think.
Yeah, they are artificial in that case, yes.
No, there's no.
But they're artificial in the sense that actually there are let's say, in the final diagrams you create these poles, which is,
Yeah. No, there's no.
Other questions? So let's skip.